We know that the heat transfer rate between two black surfaces can be expressed as the difference between their emissive powers divided by the geometric resistance. And we know that this geometric resistance is specified in terms of the view factor. For non-black surfaces, we'll show that an additional resistances associated with the surface properties must be considered. We'll also show that the heat transfer rate for these non-black surfaces in the diffuse gray limit can be defined in terms of the difference in the surface radiosities divided by the geometric resistance. So the thing that we need to really think about now is how do we incorporate the surface properties epsilon 1 and epsilon 2 into an overall resistance statement, and how do we tie these to the overall driving potential in the system, which oftentimes is simply the blackbody emissive power. So there's some surface resistance associated with surface 1, some surface resistance associated with surface 2. The total heat transfer rate between 1 and 2, we want to define it in terms of the difference in between the blackbody emissive power, where we have both the geometric resistance and the surface resistances in play. As we just noted, we imagine that there are two resistances: a surface resistance that's associated with the emissivity of each of the surfaces, and geometric resistance. To find this total resistance, we use energy balance ideas. And first of all, we need to think about what it means for this surface resistance. And to really understand the surface resistance, we do a surface energy balance. In the surface energy balance, we consider the incident radiation or irradiation on surface I or surface 1, and we think about the radiosity. So again, J is the radiosity, which is the total radiation leaving the surface. G is the irradiation or incident radiation. If this were a black surface, J is identically equal to EB, but we're not dealing with black surfaces now, we're dealing with gray diffuse surfaces. So the diffuse is useful because it has a similar property as the black surface in terms of the incident radiation and the outgoing radiation not being directionally dependent. The gray approximation says that we don't have spectral dependence. So the gray means that no spectral effects. What that means is that epsilon is not a function of lambda and alpha is not a function of lambda. So diffuse is no directional dependence, and gray is no spectral dependence. What this means is that alpha is equal to epsilon. Total hemispherical absorptivity is equal to total hemispherical emissivity. So you can see by the surface energy balance that we're showing here, N is equal to out. So this Q over A is just the heat flux that's applied to maintain the temperatures and to maintain the system at equilibrium. So N is equal to out. It says that Q plus G is equal to J, or said differently, Q is equal to J minus G. And so to identify this, the radiosity from the ith surface, Ji, as we know, is equal to the emission plus the reflected irradiation. We just looked at this global energy balance, and the global energy balance simply said that for that surface I, Q is equal to Ji minus G. Because it is a diffuse gray surface, epsilon is equal to alpha, rho plus alpha is equal to 1, and that means that rho can be thought of as 1 minus epsilon. Obviously, this is simply just the rho I, and so Ji is equal to Ei plus rho I. We've taken rho I as 1 minus alpha I, and we can write the emissive power in terms of the black body emissive power and the radiosity. So all we're doing is we're really just modifying this slightly. We understand that this Ei can be thought of in terms of epsilon I Ebi, and this is just a definition of the emissivity. The emissivity is the emissive power from the real surface divided by the emissive power from a black body. What's interesting, though, is that just understanding this is our definition of J. This is the definition of the radiosity. But we also know that Q is equal to J minus G. So we have these two equations in terms of our parameters of interest, J, G, and Q. And what we want to do is we're going to, and so here's our relationship in terms, this heat flux relationship in terms of G. And we're going to substitute this G into this equation. And so we see that we substitute G, the radiosity, as Ji minus Q. What we're going to do, because we want to come up with resistance, is we want a relationship that tells us that Q is equal to some change in some potential, we haven't defined that yet, divided by, again, the surface resistance. So let's take a look at what that change in this property is going to be. So specifying the radiosity in terms of the heat flux and the black body emissive power, this is just a continuation of what we had earlier. We can rewrite this in terms of the heat flux, and we see the heat flux can be specified, and this is not as convenient a form. We'll simply multiply this by 1 minus epsilon I Ji plus epsilon I Ebi divided by 1 minus epsilon I. So all I did was make sure that there's a common denominator for these. And so this is what we show here. And we just, it's algebra, just get rid of things that cancel things out and simplify it. And we see that Q, the heat flux, is specified as a difference in potential between the black body emissive power and the radiosity. So that change in potential that we were questioning before is Ebi minus Ji. What we now see is that the denominator can be thought of as our surface resistance, and this is 1 minus epsilon I over epsilon I. So the interpretation is the net heat flux, the net heat current that leaves surface A provided by an external agent, for example a heater, drives a current across a potential difference Eb1 minus J1 with a resistance that's a function of the emissivity. And so this is very, very powerful, and this completes the problem for us in many respects. So we know already that there's a geometric resistance, and that geometric resistance was simply associated with the view factors. That is the ability of two surfaces to see each other. Now what we've done is we've said that on top of that resistance, we would like to add the surface resistance. For a non-black surface, it's important to recognize that the radiation leaving the surface, the potential on the surface, is actually in terms of the radiosity. For these non-black surfaces, for these gray diffuse surfaces, what we have is we have an expression for Q in terms of the potential difference on surface I, the difference in potential between surface I and surface J, and the geometric resistance, and the potential drop divided by the surface resistance of surface J. So this is surface I, this is geometry, this is surface J. We know very well that whenever we have, this is the standard representation for a series problem. And that whenever we have this representation for a series problem, the simple thing that we can do is we can add the resistances, add the parameters all the way through. Said differently, Q is equal to EBI minus JI over RSI, which implies that Q RSI is equal to EBI minus JI. We can do the same thing for the other surfaces. So Q times R geometric is equal to JI minus JJ. Q times RSJ is equal to, and this is a typo actually, is equal to JJ minus EBJ. So I have a sign error here. When we sum this up, and that's how we know there was a sign error, we have Q times RSI plus RG plus RSJ is equal to EBI minus EBJ, or Q is equal to EBI minus EBJ over the sum of the resistances. And so this is a very powerful way of thinking about this problem. Make sure that you understand the correspondence. This is RSI or RS1 in this notation. This is the geometric resistance. And this is RS on surface 2. Note the potentials. The overall driving potential drop is between EB1 and EB2. The intermediate potentials are the radiosities. We can obviously also write the heat transfer rate in terms of the total potential drop, which is what we did, and we can go between the EB1, EB2 representation and using Stefan Boltzmann's formula, where these EB1 and EB2 are just specified in terms of sigma T1 to the fourth, sigma T2 to the fourth. And I'm not going to rewrite the representation for the denominator there. So this is great if you have two surfaces. So this is a simple two-surface case. We'll look at examples where we have three surfaces, where we might have, for example, a simple three-surface case, well, maybe a triangular channel where these guys all see each other. And so the way we would represent this for this triangular system is we might have EB1, J1, 1 over A1, F12, J2, EB2, 1 over A1, F13, J3, let's get rid of that. Okay. Label that J3, 1 over A2, F23, EB3. So this is as complicated a case as we can really do with the circuit analogy. For more than three surfaces, we need to think about ways of setting up linear systems of equations to solve the more general problem. So what I'm trying to show here is that I go from JI to all these different possible surfaces. Being able to represent it in a circuit is great conceptually, but it becomes much more complicated.